Hello everyone, I'm Catherine Joy Flores, and today I will teach you a new lesson that you will truly enjoy. Now, let's start our discussion. Our topic for today is all about simple machines. Every day, you use all kinds of machines. This can be simple machines like a ramp, a knife, or a pair of scissors. Do you know that machines have been used since ancient times? People have been challenged ever since to develop these machines that will make work lighter and less difficult. Machines are not only seen in factories, they can be found everywhere. In your home, the utensils your mother uses when she cooks are considered simple machines. Your school supplies, like scissors, sharpeners, and even your pencil, are also simple machines. Hundreds of years ago, when churches, houses, and many structures were built in many places in the Philippines and all over the world, no sophisticated machineries were used. These structures were built only with the help of simple machines. Simple machines served as practical solutions to our ancestors' daily struggles before. These were not meant to replace or eliminate work. Instead, they were made to make work easier and faster. Now, let us learn about the basic types of simple machines and their uses. The six simple machines that can help our work easier and not harder are inclined plane, screw, wedge, wheel and axle, lever, and pulley. Now, now, let's start with inclined plane. An inclined plane makes it easier to move things up or down. Imagine trying to carry a heavy box straight up, but if you slide it up a ramp, it's much easier. An example of inclined plane is a slide. As you can see, it makes coming down so much easier. Not to mention fun. Here are some other examples of inclined plane. We have stairs and escalators. Let's proceed to other basic type of simple machines, which is the screw. A screw is a twisted inclined plane. It helps to hold things together, like when you use a screw to attach two pieces of wood. For instance, you want to hang a picture on your wall. Will you use a screw hook or will you just punch a nail halfway into your wall? It will be better if you use a screw hook because it can be removed and put it back easily on the same hole without damaging the wall. With the nail, you will need a hammer to pull it out. If you need to put it back in, a new hole will have to be made. So, a screw is actually a spiral inclined plane. It is composed of a cylindrical body with a spiral ridge called thread. The thread surrounds the cylindrical from the tip to the head. A screw increases the force but a longer distance. Screws used friction. For a metal screw driven into wood, there is a lot of friction between the wood and the metal thread. A screw with a steeper thread can be embedded deeply into a surface with fewer turns. A screw with less steep threads require a lot more turns to driven into a surface. An example of a screw is a light bulb that uses a screw to keep the parts together. Another example of a screw is a jar lid and bolt. Now, let's proceed to the next simple machine. Here we have wedge. It is like a sharp tool with a slanted edge in which they have wedges that help cut through things by separating them apart. An example of wedge is an axe that uses a wedge to help make cutting an object easier. Another examples of wedge are nails and knife. Now, let's proceed to wheel and axle. The wheel and axle work together to help things move from one place to another more easily. The wheel and axle is a machine that has a small disc or shaft called an axle that is attached to a wheel. The wheel may be a complete wheel or a crank that turns like a wheel. When the axle turns, the wheel also turns. Now, the center of the axle is the fulcrum. The radius of the axle is the resistance. A wheel and axle can change the direction of the force. It is more effective if there is a greater difference between the wheel and the axle. A bicycle is an example of a simple machine that uses a wheel and axle to help make moving around more easy. Another example of wheel and axle are doorknob and steering wheel. Now let's proceed to lever. A lever helps us lift heavy things with less effort. It's a long board that moves up and down on a support. When you push down on one end, the other end goes up. An example of lever is a wheelbarrow, in which it uses a lever to help make lifting things easier. Now, let me tell you that lever has three parts. It's the fulcrum, load, and effort. The fulcrum is the supporting point of the lever. Effort is the force used to cause movement, while the load is the weight being moved or lifted. There are also three classes of lever based on the positions of the effort, load, and fulcrum. Let's proceed to the classes of levers. So the first is the class 1 lever. So class 1 lever has its fulcrum located between effort and load. The effort and resistance moved in opposite directions. So examples of class 1 lever are crowbar, scissors, and pliers. Next is the class 2 lever. In class 2 lever, it has the load between effort and fulcrum. The effort and resistance move in the same direction. And examples of class 2 lever are wheelbarrow and bottle opener. Now let's proceed to the next. We have here the last, which is the class 3 lever. In class 3 lever, it has the effort between the load and the fulcrum. Effort and resistance move in the same direction. Examples of class 3 lever include fishing rod, tweezers, and thongs. Now, let's proceed to the last type of simple machines. We have the pulley. A pulley is like a special kind of wheel with a groove and a rope or a chain. You can use it to lift heavy things by pulling the rope down. A flag, a flag, a flagpole is a simple machine that uses a pulley system to help make moving straight up and down easier. So pulley has different kinds, and it includes the first is the fixed pulley. In fixed pulley, it is attached to a hook or a wall and it doesn't move. Next is the movable pulley. It is free to move up or down and is attached to a ceiling or other objects by two lengths of the same rope. And an example of movable pulley is the construction cranes. And last kind of pulley is the block and tackle pulley. Here, it is a combination of the movable and the fixed pulleys. Those things are all example of simple machines that we can see everywhere. Now, is there anyone who wants to ask questions? If none, then let's see if you truly know and remember all the types of simple machines through this activity entitled. In this activity, you just only have to match these simple machines based on its type. I will give you time to answer. Now, let's check if your answer are all correct. In the first, we have wedge, screw, inclined plane, lever, pulley, and wheel axle. Very good, everyone. It seems that everyone learned in this topic. That's all for now, and prepare for our next topic, which is all about the properties of water waves.
Good day everyone, I am Jello and Ischoco. Today, I will talk about water waves and their properties. Water waves are important part of our world. We see them in oceans, lakes, and even in small puddles when it rains. But what exactly are water waves? Let's find out. Now, let's know what is wave. A wave carries energy from one place to another, but the water itself does not move with the wave. It only moves up and down. This is why if you drop a stone in water, you see ripples that spread out, but the water itself does not travel far. How are water waves formed? Water waves are made when the wind blows over the surface of water. The stronger wind, the bigger the waves. Other things like earthquakes or throwing an object into water can also create waves. Now, to the properties of water waves. Water waves have special properties that help us understand how they behave. Reflection. So, reflection happens when a wave hits a barrier, like a wall or a side of a pool. It bounces back. So, one of the example is if you throw a rock into a pond near the edge, you will see waves bounce back from the side. So, the next property of the water waves is refraction. It happens when a wave moves from deep water to shallow water. It changes direction and speed. And one of the example is when waves move from the deep sea to the shore, they slow down and change shape. Next is diffraction. It happens when a wave passes through a small opening or around an object. It spreads out. So, example, when ocean waves hit a rock with a hole in it, the water spread out on the other side. So, next property is wavelength. The wavelength is a distance between two crests, the highest points of waves, or two through the lowest points. Bigger waves have longer wavelengths. The smaller waves have shorter wavelengths. Next is frequency. This tells us how many waves pass a point in 1 second. If many waves pass quickly, the frequency is high. If they come slowly, the frequency is low. Now, let's go to investigating water waves with a ripple tank. Scientists use a ripple tank to study water waves. This is a special tank filled with water. When we make waves in the tank, we can see how they move and behave in a ripple tank. We can observe reflection. Waves bounce back when they hit a barrier. The refraction. Waves change speed when moving from deep to shallow water. Next property that we can observe is diffraction. Waves spread when they pass through gap or moves around an object. So, let us know why are water waves important. Water waves are important in nature and science. They help us understand how wave moves in ocean, how sound and light waves work since they behave in similar way, and how they build a safe structures like bridges and boats that can handle strong waves. So, let us always remember that water waves are more than just what we see at the beach. They have different properties like reflection, refraction, diffraction, wavelength, and frequency. And the scientists use ripple tanks to study them. And they are important for many things in our world.
So, good day everyone. My name is Gloridine Bigalam and I will be discussing the properties of sound waves. So, in this report, I will explain the key properties of sound waves such as wavelength, amplitude, frequency, velocity, and time period. So, I also provide real-life examples to make this concept easier to grasp. So, properties of sound waves. Sound waves are a fundamental aspect of the world around us, and understanding their properties help us grasp how sound travels and interacts with different mediums. So first, I will discuss about the sound wavelength. So the wavelength of sound refers to the distance between two consecutive compressions or rarefactions. So compressions this is about where the particles are pushed together. So it is compression. And the rarefactions, the areas are spread apart. So compression, they are pushed together. Rarefactions, they are pushed, they are spread apart. So the wavelength is the length of one complete cycle of compression and rarefaction. So I have here an example. So if you have a guitar at your home, or you know how to guitar, so if you will look at the sound wave produced by a guitar, the distance between two consecutive peaks, or yung pag ginanon mo siya, it is the compressions. So as I said a while, compressions is they are pushed together. So it is represent the wavelength. So another example, may dalawang taong tumatalon up and down, and nagsisync sila sa pagtalon. So, yung distance nila between one person and the next as they jump and down represents the wavelength. So, in sound, this would be the distance between the compressions, or when the air particles are pushed together, kapag tumatalon sila, yung wavelength dun is yung hangin. And kapag tumatalon sila up and down, the particles are pushed together. I know, kapag tumatalon sila ng sabay, in sync, the particles are pushed together. Or, yung rarefactions naman, kapag tumatalon sila up and down, the particles are spread apart. So, that is the sound wavelength. So, next is the sound wave amplitude. Amplitude describes the height or size of the sound wave. So, in amplitude, it describes the height or yung size ng sound wave. It is the maximum displacement of particles in the medium from their resting position as the sound wave passes. Larger amplitudes correspond to louder sounds, while smaller amplitudes produce softer sounds. So, example, when we clap ng loud, so we hear that it has a higher amplitude. Kesa kapag pabulong, it has a softer amplitude. The bigger the wave's amplitude, the louder the sound we hear. So next is, another example. Think of a gentle breeze versus a strong wind. The gentle breeze is like a small sound wave with low amplitude. Kapag yung yung hangin lang na mahina, it has only low amplitude. Kapag naman malakas yung hangin, like parang buhawi ganon. So mas malakas yung amplitude nun. So mas large yung sound wave niya with a high amplitude, creating a louder sound. So that is amplitude. So next is we have the frequency. Frequency is the number of complete waves that pass a point in 1 second, measured in hertz or Hz. A low frequency sound has fewer waves per second, producing a deeper bass-like sound, while a high frequency sound has more waves per second and sound higher pitch. So, example, yung sound ng ambulansya, 'di ba maingay 'yon? So it has a high frequency sound, which makes it easy to hear quickly, as well as the beeping sound of cell phone or alarm. So, 'di ba pag nag-a-alarm tayo, madali tayong magising kasi malakas yung kanyang frequency sound. So, on the other hand, yung tunog ng kambing at saka baka, mababa lang yung frequency niya. Unlike dun sa tunog ng yung wawang ng ambulansya, madali siyang marinig, which is, it has a higher frequency sound. So, next naman tayo ngayon is time period. So, time period, it is the inverse of frequency. It refers to the time it takes for one complete cycle of a sound wave to pass a point. A longer time period corresponds to a lower frequency and deeper sounds. So, kapag mas mahaba yung time period, mas mababa yung frequency and yung lalim nung tunog. While a shorter time period correspond to a higher frequency and higher picture sound. So, ano ba example nito? So, example is, the ticking of a large clock produces a longer time period than the ticking of a small, fast-moving clock. So, sa larger clock, mas nakakapag-produce siya ng mas mahabang time period kesa dun sa small, fast-moving clock. So, moving on to velocity. Velocity or speed is how fast a sound wave travels through a medium. So, it is measured in meters per second. The velocity of sound depends on the medium it travels through. Sound moves faster and denser materials like water or steel compared to the air. So, example, kunyari nasa ilog tayo. Kapag nag-throw tayo ng bato sa water, maririnig natin yung splash niya, yung pag ginano mo siya, maririnig natin yung ganong sound. You'll hear the sound faster underwater than you would in the air. Sound travels faster in water than in air. So, mas mabilis nagta-travel yung sound sa water kesa dun sa air. That's why sounds are clearer underwater, like in submarines or while diving compared to above the surface. So, that's it for the report about the properties of sound wave.
So, good day everyone. I am Jessery D. Guillermo and I will be discussing the longitudinal waves and transverse waves. So, first is the longitudinal waves. And what is longitudinal waves? Longitudinal waves, it is a wave in which particles of the medium move in a direction parallel to the direction that the wave moves. Suppose that a slinky is stretched out in a horizontal direction across the classroom and that a pulse is introduced into the slinky on the left end, vibrating the first coil left and right. The energy will begin to be transported through the slinky from left to right. As the energy is transported from left to right, the individual coils of the medium will be displaced leftwards and rightwards. In longitudinal waves, the energy is transferred through compressions and refraction. In this case, the particles of the medium move parallel to the direction that the pulse moves. This type of wave is longitudinal wave, and it is always characterized by particle motion being parallel to the wave motion. Longitudinal waves, it is also known as P waves. It is refers to waves in which the direction of propagation align with the direction of vibration of the medium. These waves are responsible for the intense sounds heard during major earthquake, and it can travel at speed of approximately 5 miles per second. And we have 7 examples of longitudinal waves. And the first one is the sound waves. Sound waves are vibrations that travel through a medium like air, water, or metal. They are created when an object vibrates, which compresses or rarefies the air molecules around it. And how sound waves work? When you clap your hands, the air molecules between your hands compress. This compression travels outward and reaches your eardrums. The vibration in your eardrums signal your brain, which interprets them as sound. And the characteristics of sound waves: amplitude, the relative strength of the sound waves which we perceive as loudness or volume. Amplitude is measured in decibels. The next one is the wavelength, the distance between identical points in a sound wave, and the frequency, the number of rare fractions and compressions per unit of time. And the second example is the ultrasound waves. Ultrasound waves are high-frequency sound waves that are used to create images of internal organs and tissues. They are used in a variety of medical and industrial applications. And how ultrasound waves are created. An electric current is applied to piezoelectric crystals which causes them to vibrate and produce sound waves. The sound waves are sent out in pulses. The sound waves reflect off tissue boundaries and return to the transducer. The transducer detects the echoes and sends electrical signals to the ultrasound scanner. And how ultrasound images are created. The scanner uses the speed of sound and the time it takes for the echoes to return to calculate the distance to tissue boundaries. These distances are used to create two-dimensional images. And the third example is the seismic P waves. Seismic P waves, also known as primary waves or pressure waves, are the fastest type of seismic wave that travels through the earth, arriving first at a seismography station after an earthquake due to their high speed. They are compressional waves, meaning they cause particles in the medium to vibrate back and forth in the same direction as the wave is traveling, allowing them to move through both solid and liquid materials like the Earth's core, unlike the slower S waves which can only travel through solids. And the fourth example is the tsunami waves. A tsunami wave is a series of extremely long ocean waves generated by a sudden and large displacement of water, typically caused by underwater earthquakes, volcanic eruptions, landslide, or meteor impacts, which can travel at high speeds across the ocean and become significantly taller when reaching shallow coastal waters, causing destructive flooding on land. Unlike regular waves, tsunamis move through the entire water column, not just the surface, and can be very destructive due to their immense size and force. And the fifth one is the waves in solid. Waves in a solid are disturbances that propagate through the material by transferring energy from one particle to another, occurring because the particles in a solid are tightly packed together, allowing vibrations to travel quickly and efficiently, making the speed of sound in solids much faster than in liquids or gases. These waves can be either longitudinal waves where particles vibrate parallel to the wave direction, or transverse waves where particles vibrate perpendicular to the wave direction, with a specific type of wave depending on the solid's properties and the nature of these disturbances. And the next example is the pressure waves in gases. A pressure wave in a gas is the longitudinal wave that occurs when the gas molecules are compressed and then rarefied, causing a traveling disturbance of pressure changes as the energy propagates through the gas. Essentially, it's a wave of alternating high and low pressure regions created by the collision and movement of gas particles, most commonly observed as sound waves. And lastly is the spring vibration. A spring vibration in waves refers to the back and forth movement of a spring when disturbed, creating a wave-like pattern where the coils of the spring alternately compress and stretch, essentially acting as a medium to transmit energy through the spring in the form of a longitudinal wave. This motion is often described as a simple harmonic motion due to the restoring force of the spring being proportional to its displacement, resulting in a consistent oscillation pattern. And now is the transverse waves. And what is transverse waves? Transverse waves, it is a wave in which particles of the medium move in a direction perpendicular to the directions that the wave moves. Suppose that a slinky is stretched out in horizontal directions across the classroom and that a pulse is introduced into the slinky on the left end, vibrating the first coil up and down. The energy will begin to be transported through the slinky from left to right. As the energy is transported from the left to right, the individual coils of the medium will be displaced upwards and downwards. In transverse waves, energy is transferred through the movement of the medium's particles in the directions of the wave. A transverse wave is a type of wave where the particles of the medium vibrate perpendicular at a right angle to the directions the wave is traveling, meaning the wave motion is up and down while the wave itself moves horizontally. A common example is the wave created by shaking a rope up and down, where the rope particles move vertically while the wave travels along the rope's length. And the transverse waves consist of the crest and trough. The high points of a transverse waves are called crest and the low points are called trough. Amplitude of the transverse wave is the maximum displacement of a particle from its equilibrium position. And the wavelength, the distance between two consecutive crests, is called the wavelength. And we have 5 examples of transverse waves. The first example is the ripples on the surface of water. When you see ripples on the surface of water, you are observing transverse waves, meaning the water molecules move up and down, perpendicular to the directions the wave travels. As the wave energy propagates horizontally across the surface, creating the visible ripples with crest or the high points and through the low points. As the disturbance spreads outward from the source, like when a stone is dropped into a pond. Essentially, the water molecules oscillate vertically while the wave itself moves horizontally. The second example is the vibrations on a guitar string. When a guitar string is plucked, it vibrates in a transverse wave pattern, meaning the string moves up and down, perpendicular to the directions the wave travels along the string, creating the characteristic wave-like motion you see when a guitar string is played. Essentially, the string oscillates at right angles to the directions of wave propagation, generating sound waves in the air. And the third example is the Mexican wave in a sports stadium. A Mexican wave in a sports stadium is considered a transverse wave because the movement of the people standing up and sitting down happens perpendicular to the directions the wave appears to be traveling, meaning the vibrations or the people standing occur at the right angles to the wave propagation or the wave moving across the stadium. Essentially, the people move vertically while the wave moves horizontally, which is the defining characteristic of a transverse wave. And the fourth example is the electromagnetic waves. An electromagnetic waves refers to a disturbance in the electric and magnetic field that propagates through space, transferring energy from one point to another. It can be described in terms of parameters such as wavelength, amplitude, frequency, and phase. And how are they created? Electromagnetic waves are created when charged particles like electrons vibrate. The vibrations of charged particles emits energy in the form of electromagnetic radiations. And lastly is the S waves. S waves, also known as secondary waves, are seismic waves that move the ground back and forth in a shearing motion. They are the second type of body wave that you feel during an earthquake. And how S waves move? S wave moves are slower than P waves. S waves move perpendicular to the directions of wave propagations and can only move through solid materials, not liquids. And S waves shakes particles from the side to side.